Let's hope I remember it, because I wrote the wrong notes. Okay, so what's important in perturbation theory is to understand the distinction between singular and regular perturbation theory. Okay? So for example, when we started in our first, in the first lecture, we presented the equation x to the 5 plus epsilon x equals 1, and this was a regular perturbation theory. Okay, let's explain why. Because as epsilon goes to 0, we have here 5 answers, right? The 5 answers are, we start with okay, we can write x as sum from n equals 0 to infinity of a n epsilon to the power of n. And now we have to calculate the a's, right? And it turns out that a0, for example, if I'm taking, so to 0's power in epsilon, I have x to the 5 equals 1, which implies that, for example, x is 1. This is one of 5 solutions, right? Because I have here, this is a 5th order equation, I have 5 solutions, but this is one solution. Then I can write, so this is 1 plus a1 epsilon plus a2 epsilon squared, and so on and so forth, right? And now if I would like to calculate a1, I will plug it here, and I will find that 1 plus a epsilon a1 to the power of 5 plus epsilon times 1 plus epsilon a1 equals 1. Now, I have to expand it to keep only first order in epsilon. So what I will get is 1 plus epsilon times 5a1 plus 1, right? This is equal to 1. The 1 and the 1 cancel. Okay?
No.
I expand this and I keep only...
One is 0th order of epsilon.
Yes. So to the first order in
no,
epsilon...
on the right side. On the right side of the equation.
Ah, sorry.
Should be
Yes.
0.
No, but I have an epsilon here. I have an epsilon here. This is x.
Yes, but it's still on the left side. On the right side you should have 0. Oh, wait. No.
I expand this.
Yes, but you next.
This is 1 plus 5 epsilon a1.
Ah, okay.
And this is epsilon, and this will go like epsilon squared. So if I find that that a1 is minus 1/5, and if I remember it correctly from the first lecture, then a2 was 1 over 25, and a3 was 1 over 125, and so on and so forth, right? Which implies that in general x will be, yes, 1 plus minus epsilon over 5 plus epsilon squared over 25 minus maybe epsilon cubed over 125, and so on and so forth. And the point is that the answer, when you take epsilon to 0, you get the 0th order answer. You see? This is a regular perturbation theory. So in a regular perturbation theory, x of epsilon, so this is x of epsilon, yes, is a smooth function of epsilon at the vicinity of epsilon when epsilon goes to 0. You see?
Shouldn't epsilon goes to 1?
No, epsilon, okay, no, I expanded it now around, okay, now the question is, can I put epsilon equals 1 and sum the series? That's another question.
Can
right?
you?
What?
Can you?
I think that yes. I I gave the details in the first. So now the question is, what's the radius of convergence? Yes, but at least x converges to the right answer when epsilon goes to 0. So, I mean, physically speaking, if I have no perturbation, suppose this is perturbation, right? If I have no perturbation and I have small perturbation, then I will get small deviation from the answer. Yes?
Does x converges to the right answer even on the complex plane or just on the real plane?
I think that if it converges, it's a Taylor series, so it has a finite radius of convergence.
No, but if epsilon goes to 0,
yes,
will it converge to the complex solutions as well as the
yes,
solutions?
yes. Okay, so this is a regular, in that sense, this is a regular perturbation theory. Right? On the other hand, if we think about the following equation, epsilon squared times x squared, x to the power of 6, plus epsilon times x to the power of 4, maybe there is a minus, minus x cubed plus 8 equals 0. Right? So, what is the zeroth order solution? The zeroth order solution, as it stands, is a solution I will find when epsilon is 0. So what are the zeroth order solutions? We have 3 solutions, right? The zeroth order solutions are the solution of x cubed equals 8, right? x0 cubed equals 8. So x0 may be 2 or 2e to the I 2 pi over 3 or 2e to the I 4 pi over 3. Right? That's the 3 solutions. You agree with me? Okay. Now, how many solutions the one equation have? 6. So there are 3 solutions, right? For any finite epsilon, there are extra 3 solutions that are not here. Where they are? What these solutions are doing when epsilon is going to 0?
Some solution times epsilon.
What?
It's some solution times epsilon. Where epsilon goes to 0, it's...
So you are saying they are going to 0, but 0 is not a solution because I have an 8 here.
Wait, why did you wrote a 4 pi over 3? Why didn't you wrote minus 2?
That's the same.
Yeah, it's the same.
Okay? So, you see what's happened? And indeed, okay, so what we should do, in order to find the other solutions, we should use the principle of dominant balance. So we are saying for any, when epsilon goes to 0, right, I wonder what are the 2 terms, I guess that out of 4 terms, right, when epsilon goes to 0, only 2 of them will be the important terms that will cancel each other to give 0. Why? Because why not? It should be a miracle for that 3 terms will do that, right? So, and I demonstrated this in the first lecture of the semester, but I will just tell you that the answer is that these are the 2 terms that are the leading terms in the dominant balance. So first of all, let's assume that this is true. If this is true, then epsilon squared x to the 6 minus x cubed is asymptotic to x cubed as epsilon goes to 0, which implies that x is asymptotic to epsilon. So, okay, so either x is 0, or I can cancel and I get epsilon squared x cubed. Let me write it. Is asymptotic to 1, so x is asymptotic to epsilon to the minus of 2/3. Right? That's the answer. Let's just check for consistency. If x is going like epsilon to the minus of 2/3, then as epsilon goes to 0, right? This will be epsilon to the minus 2, and this will be epsilon to the minus 2. So they will diverge, like epsilon to the minus 2. Now, this term is a constant, so it will not diverge as epsilon goes to 0, right? And this term will behave like epsilon times epsilon to the minus 8/3. So it's epsilon to the minus of 5/3. They diverge slower as epsilon goes to 0. So the dominant terms will be these two.
Slower?
What?
Even it's not faster?
No. 1 over epsilon squared diverges much faster than 1 over epsilon. The lower is the power, the negative power, the slower is the divergence. Okay? So, and okay, you can check that if you will try to use these two terms for the dominant balance, you will find out that, right? For example, okay, let's do another example. Let's take these two terms for the dominant balance, which implies that x is going like epsilon to the minus 1. You see? But if x is going like epsilon to the minus 1, 8 is negligible as epsilon goes to 0. But this epsilon squared times x to the 6 will go like epsilon to the minus 4, which diverges much faster than epsilon to the minus 3, than this term.
But can't you say that only 8 is negligible and all the other terms are not negligible?
Sorry?
Isn't any, you can't say that 8 is negligible but all the other terms are not negligible?
No, because as I told you, generically, there is, unless a miracle happened, yes, generically, only two terms will balance each other as epsilon goes to 0. Right? Now, you may say, okay, let's choose here, let's have another equation, where here I will put, instead of epsilon times x to the 4, I will put epsilon to the 4/3, to the 2/3 times x to the 4. And then if x is going like epsilon to the minus 2/3, this term will be epsilon to the 2/3 times x to the minus 8/3, right? Okay, because this is epsilon to the minus 2/3 to the power of 4.
Epsilon, okay.
Epsilon, sorry, epsilon to the minus 8/3, which is epsilon to the 6 to the minus 6/3, which is epsilon to the minus 2, and then it will be the same power as this and that. This may be, but I had to, to fine-tune the system in order to do that. So it may happen that all three terms are important, but the generic case is that only two of them are important when as epsilon goes to 0. Okay? And now, to continue, right, to have a regular perturbation theory, so this is a singular perturbation theory. How do I make it a regular perturbation theory? Very simple. I will define y. I will define a new y to be what? To be x times, sorry, I will define x to be y times epsilon to the minus 2/3. Now this implies that as epsilon goes to 0, x diverges, but y stays over 1. That's the logic, right? And then I can write the equation for y. So the equation for y is epsilon squared times y to the 6 times epsilon to the minus 4. You see? This is this term. Plus what? Sorry, minus epsilon times y to the 4 times epsilon to the minus 8/3 minus y to the 3 times epsilon to the minus 2 plus 8 equals 0. This is the new equation in terms of y. Okay? And this equation, what this equation is doing, right now you can see that I have epsilon to the minus 2 here and epsilon to the minus 2 here, which are the most fastly diverging terms as epsilon goes to 0. So the way to proceed is to multiply everything by epsilon squared, right? And then what we will get is y to the 6 minus y to the 3. Both of them are now epsilon free terms. And now I have minus. Here I have epsilon to the minus 8/3. And this is epsilon, so it will be epsilon to the minus 5/3. Multiplying by epsilon to the power of 2, I will get epsilon to the power of 2/3.
2/3?
No, 1/3.
Of 1/3. Yes, 1/3. Times y to the 4 plus epsilon squared 8 epsilon squared equals 0. Okay? Now this is a regular perturbation theory. Right? This was an example of singular perturbation theory. Right? Okay? And now we have a regular perturbation theory. What makes the difference between regular and singular? Usually, the question is whether or not epsilon is in the coefficient of the highest power. Because you know that if you have the number of solutions is equal to the highest power. Right? That's the basic principle of algebra. Okay? And when epsilon goes to 0, if the highest power disappears, what it implies? It implies that now at epsilon goes to 0, the number of solution is smaller than the true number of solution for any finite epsilon. Right? And so this is a singular perturbation theory, because for any finite epsilon you have 6 solutions. For finite epsilon you have, for 0 epsilon you have 3 solutions. Yes?
But in the new equation, if you solve it without epsilon, you mean just neglect the epsilon, you get less than 6
Wait, no,
solutions.
no.
No, without epsilon.
What I will get now is, if now I am taking epsilon to 0, this is your question, I will get 6 solutions. Why 6? I have 3 zeros, because what I will get is y to the 6 is equal to y to the 3.
That's my question. The other solution just merge to one.
No, wait. I have 3 solutions that are 0, and now after counting these 3, I can take here y,
No, it's 1.
what?
It will be equal to 1.
Yes. And I have 1 e to the I 2 pi over 3 and e to the I 2 pi over 6. Right? Now, what are the actual solutions in terms of x? You remember what are they? The relationships are here.
כן, זה 4/3.
What?
It's
4 over 6.
Four, what I wrote?
2 pi over 6.
Oh, sorry. 4 pi over 6. Sure. Okay? So, you see what's happened. when we took this epsilon to be 0 here in the purple equation, we obtained three solutions that are the three roots of 2 times 3 roots of 1. Okay? Now, these three solutions are finite, and then we make this substitution. Okay? So in order to translate this to x, this is not 1. This in x, this is 1. This is epsilon to the minus 2/3. Right? So this is a solution that goes to infinity as epsilon goes to 0. You see? So, and why these are zeros? These are zeros because these are these three solutions that are finite in x, but if you multiply them by, if you multiply now their y is 0, right? Because y is x times epsilon to the 2/3. So y goes to 0, when x is finite, y goes to 0. You see? So these are three solutions, and these are the other three solutions. These are the three solutions that go to finite number as epsilon goes to 0. And these three solutions are going to infinity as epsilon goes to 0.
So you get other solutions.
So if you look at the complex plane, so real x and image x, right? You have 6 solutions, 3 of them are approaching finite number as epsilon goes to 0. The other 3 no, sorry, this is 1 and okay. So doesn't matter, right? Okay. The other 3 are going to infinity as epsilon goes to 0. So this is the general structure of a singular perturbation theory. Some of the solutions are going to infinity as epsilon goes to 0, instead of going to these points. Yes?
Shouldn't the solutions of the green equation be 0, 1, and minus 1? Because
What?
the solution for the green equation shouldn't be just 0, 1, and minus 1? Y to the third is equal to y.
No, it's 1.
No, it was y to the 6th. I started with y to the 6th equals to y to the 3rd. This is
Okay.
the equation. Now it has degeneracy. So you have 3 zeros, right? Every time you cancel y from both sides. And then after doing that, you get y to the 3 equals to 1. So this
okay.
was the equation. Yeah, sure. Equals to 1, that gives you that. Yeah, of
How
course.
can you restore the solution to the original solution?
What?
How can you restore the
Here, these are the relationships.
yes, but here you got
Now, if you want, for example, okay, if you want to calculate the correction to this solution, to 1, say, okay, then now I will write y equals 1 plus epsilon to the 1/3. Note that when we have singular perturbation theory, the expansion is not in integer units of epsilon. Not necessarily.
Plus, not minus.
1 plus epsilon third times a1, say, or y1. Okay, y times a1. Right? And I would like to plug it here. Okay? So what I will get? I will get from here, I will get to the order of epsilon to the 1/3. Right? Okay. I will keep only terms, okay, let me write it. I have 1 plus epsilon to the 1/3 a to the power of 6 minus 1 plus epsilon to the 1/3 a to the power of 3 minus epsilon to the 1/3 times 1 plus a, a1, I call it, okay? Epsilon to the 1/3 to the power of 4 plus 8 epsilon squared equals 0. Okay? Now, if I'm taking everything that is epsilon to the power of 0, then I have 1 minus 1 by construction. Okay? If I'm taking the epsilon to the 1/3 terms, what I will have? I will have from here 6a1 minus from here 3a1 minus from here
Minus
1 equals 0. Right? This will not join the celebration yet. This will enter only in the 6th order in the perturbation theory. Right? I have epsilon to the 1/3, to the 2/3, to the 1. This will enter only in the 6th iteration. But before that, I will get this, and this implies that A1 is 1/3. Right? So the actual solution.
You
What?
skipped all the you skipped opening those ugly.
I'm looking only for things that are order epsilon to the 1/3.
No, I said you skipped opening all the other terms, finding epsilon, the other terms for
Because this will give me epsilon to the 2/3 and so on and so forth.
Yes.
Okay? So this implies that to the first order in perturbation theory, y is 1 plus epsilon to the 1/3 over 3. Right? Where again, this will correspond to x, which is 1 over epsilon to the, or epsilon to the minus 2/3, that goes to infinity, plus epsilon to the minus 1/3 over 3. Yes. And this one goes faster to infinity than that one.
So the next solution, the next perturbation,
You want me to write here plus epsilon to the 2/3 times A2 and to calculate A2. Right?
don't you want to find the epsilon to the power of 2 also?
That's the 6th order in perturbation theory. You can do that, but it's a lot of work, as usual.
My question is, when would you notice all the six solutions for x?
Here, you have 3 of them here, right? And you have the other 3 from this procedure.
No, but we say that for really small x's, like really small x's, x is divergence. That this
So very small epsilon.
very small epsilon x.
There are
is
3
divergent.
solutions that diverge and 3 solutions that converge to finite number.
Yes, but for a certain perturbation, the solution would converge. No.
No, because you have epsilon to the minus 2/3 to begin with. Okay? So I would like to use this relatively simple example in order to emphasize a few points that are generic to singular perturbation theory. First of all, we get singular perturbations usually when epsilon stands as a coefficient of the highest power, or if you have a differential equation of the highest derivative. Right? If we have a third order, I mean, you see what I'm saying, right? That's number 1. Number 2, that's number 1. Number 2, when you have singular perturbation, at least some of the solutions disappear as epsilon goes to 0. Okay? Number 3, in order to get to take care of the situation, at least when it is possible, you can change variables. You can find out from dominant balance. You can find out what the behavior of this diverging solution as epsilon goes to 0, and then find this diverging solution, and then make a transformation that yields a regular perturbation theory. And in the transformation, you want to transform it such that as x goes to infinity, y is still order 1. Okay? That's a singular perturbation theory. So again, in a regular perturbation theory, what we get is solutions that go smoothly to the right solution as epsilon goes to 0. And in a singular perturbation theory, that's apple in the maggot. I have maggot in the apple I told you about 2 lectures ago, I guess. When you take epsilon to 0, the solution diverges. Okay? Here is another example. Let's take now differential equation of the form epsilon y double prime. I've forgotten what differential equation I want to give. As I told you, I forgot my notes in my okay, maybe I can find an example in the book. Yes. So epsilon y double prime minus y is 0, where y of 0, let's say 0, and y of 1, let's say 1. Right? We have a differential equation. Now, this is a solvable problem. Why it is solvable? Why it is solvable?
What do you mean by it's just an harmonic oscillator?
Yes.
What do you mean by
Not,
solvable?
what? Not necessarily, because you have a minus here, not a plus.
Okay,
so it's
so
not
the exponents, yes. But,
Technically speaking, it is solvable because it is a differential equation with constant coefficient. And in differential equation in constant coefficient, you know that the substitution y is, equals to e to the alpha x with some coefficient will give you the right answer. Okay? If I plug e to the alpha x here, I will get epsilon alpha squared minus 1 equals 0. That's the equation. And now the solution for this, right, what is the solution? We have, wait. Maybe it's, so I have y prime here. Okay? So epsilon alpha squared minus alpha is 0. And this is not only, it's not harmonic oscillator and not inverted harmonic oscillator, it's something else. And the solutions are alpha equals 0 and alpha equals 1 over epsilon. Okay? So the general solution is y equals a plus b e to the x over epsilon. That's the general solution. Now I have to satisfy the boundary conditions. To determine a and b by satisfying the boundary conditions. And what are the boundary conditions? We want it to be 0 at 0, which implies that y is equal to a times 1 minus e to the x over epsilon. Note that as x equals 0, this will be 1. So, okay? You see what I'm saying? And now I have to make sure that at 1 it will be equal to 1, but this is very easy. I will write 1 minus e to the x over epsilon divided by 1 minus e to the 1 over epsilon. So clearly when x equals 1, this will be equal to 1. Okay, so this is the solution. Now, how this solution looks like? Here is the question. How this solution looks like, right? It should be 1 at x equals 1. It should be 0 at 0. That's the boundary conditions. 0 at 0, 1 at 1.
And the conditions are for y, not y prime.
What?
'Cause
For
it's-
y, for y, not for y prime. Now, how the answer looks like? Note that, and in particular, now I am interested in the case where epsilon goes to 0. Now, is that a regular or singular perturbation theory?
Singular.
Singular. How do I know that this is singular?
There is an epsilon.
There is only one solution.
I will say 3 reasons. Of course, it's the same thing. First of all, epsilon is the coefficient of the highest power, of the highest derivative. A. B. After I translated it to a polynomial equation, epsilon is the coefficient of the highest power of the polynomial. Okay, the same thing. C. If I'm taking epsilon to 0 naively, so just taking this term to be 0, what will be the answer for this equation? Y prime equals 0, then y is a constant. And if y is a constant, I cannot satisfy these two. There is no solution to the equation because I cannot satisfy the boundary conditions. In order to satisfy the boundary conditions, I must take y to be not constant. I must take this epsilon term. So no matter how small epsilon, the solution will be completely different if epsilon is 0 and if epsilon is 10 to the minus 100. Right? Okay? So how the solution when epsilon equals 0, how the solution when epsilon is equal to 10 to the minus 100 approaches the solution at 0? That's the question. You see what I'm asking? And the answer is that for, right, if I will define, so look at this thing, right? As long as x, if epsilon goes to 0, this term blows up and this term blows up.
They blow up like
Right?
the same rate.
So I can neglect these two terms and I will get e to the x over epsilon divided by e to the 1 over epsilon, and this will give me e to the x minus 1 over epsilon. Right? Okay?
And this is bound.
Now, if epsilon, as long as x minus 1 is, let's say, 0.0001, as long as x minus 1, absolute value, is much larger than epsilon, right? This will be, okay, x is smaller than 1 in the regime we are looking at, right? So I will write it as e to the minus 1 minus x over epsilon, okay? If 1 minus x is finite, like 10 to the minus 5, and I'm taking epsilon to be 10 to the minus 100, what will be? What I will get? 0. 0. So the answer, the solution will be 0 until 1 minus x starts to be of order epsilon. Right? So if epsilon is, say, 0.1, then it will go like that, and at 0.9, it will start shooting up. You see? And if I will take epsilon to be, sorry, if I will take, yes, and now if epsilon will be 0.01, what will happen? Right? If epsilon will be 0.01, it will go here like that, and only, sorry, and only here at 0.99, it will shut up. So you see what's happened, right? This region was the function, so we have an infinitely, as epsilon goes to infinity, we have an infinitely narrow region where the function changes its behavior with respect to the solution where epsilon goes to 0. For epsilon goes to 0, we have a solution with a constant, right, which is constant all the way, so it cannot satisfy the boundary conditions. And as epsilon goes to 0, I will develop here a region that will be as narrow as its width will be of order epsilon. And in this region, we have a completely different behavior. Right? Such a region is called a boundary layer. Right? And this is an example, again, of a singular perturbation theory. You see? So, for example, I guess the most famous example of all this science is in hydrodynamics. So, if you remember what you were taught about hydrodynamics, and if I remember it, because as I told you, I forgotten my notes. So in hydrodynamics, we have equations of the form something like, okay, we want to describe, right, the velocity field of a liquid, say water or air, gas, whatever, right? And the equation is satisfied, and it depends of course also on T. Okay? The equation it satisfies is dou V dot E plus V dot grad V V dot grad V, like that, is equal to, these are Newton's law essentially, and there are forces here. Let's write F, although usually people are writing here gradient of pressure or something, some force that is acting on the force that depend on X, Y, Z, and T also. And what's important that we have here something like ni, and the second derivative of V with respect, the Laplacian of V. Right? The Laplacian of V is a term that is called viscosity. Right? Why? Because it implies that you want V to be, if V is changing rapidly, then there is a friction between the, right? If here in this layer V is very large and in this layer V is very small, then there is a friction between the two layers and they are applying force on each other, which is that. An extra force. Now, usually what people are asking is how the velocity. So, for example, what is the most important application of these equations? These are called, I guess, Navier-Stokes equations. And what is their most famous and important applications? For example, aerodynamics. Right? You have an airplane, and you want to analyze the flow of air, that's V, around the wing of an airplane. Hopefully, the air will do something that will lift the airplane up. Otherwise, you can, the whole apparatus is not useful. Okay? And to analyze that, this is a very difficult question because the wing of an airplane is something weird, right? But to begin with, you can ask what is the flow around the cylinder. You have an infinite cylinder, and you are asking how the water are flowing around this cylinder. How the flow lines, the streamlines look like. You see? And to do that, people have noticed that you can use here, what are the, okay, you can measure, let me see if I can recover it. You can measure, first of all, far away from the cylinder, or far away from the airplane, right? The airplane, suppose, is flying at a speed of 800 kilometers per hour, right? That's a standard speed of transatlantic aviation. Okay? What's okay?
יש
So
פה טענות להפוך את המטוס לגליל.
no. I'm not trying to. What I would like to convince you in a moment, right? So essentially, of course, there is no difference between dragging the cylinder through the fluid and dragging and flowing the fluid over the cylinder, right? It's the same problem. So you can define V infinity as the velocity of the fluid far away from the cylinder, right? Far away from the cylinder, there is some asymptotic velocity of the. I mean, that's a river, right? The velocity of the fluid in the river. Okay, you have the cylinder in the middle of the river, but the river is very wide. It's the Amazon River, and far away, and of course you also neglect the edges of the river. So, I mean, there is some asymptotic velocity. Okay.
גליל הוא מקובע.
Yes. Otherwise, you can take the cylinder and push it through the fluid, but it's the same thing, right? So in which case the V infinity will be the velocity of the cylinder, right? And this is one quantity in the problem. Another quantity is the diameter of the cylinder, okay? Some length scale, okay? And do we have another? Okay, so the idea is to measure velocities as a fraction of the. Okay, to measure distances in unit of d. Right. So I want to. Okay, to measure. So first of all. Velocity is, say, dx dt, right? Okay, so I will define xc as x over d. So ddx is dxc is x over d. So v will be d dot c dot t, right? You see, c is a dimensionless quantity. Okay, so I will have every time I have v, I should multiply it by t, right? If I want to here to have it in unit, this is one thing, and now. So I will write, so everywhere I have d, I will multiply it by d, so I will have d here, and d squared here, and d there. So all in all, I have 1 over d here. Forget about this term for the moment. Right? I have 1 over d here, and all these v's are now with respect to the dimensionless, right? Now I want to measure everything, every v, in units of v infinity. You see? So, so what? So I would like to say that v is some v tilde, which is dimensionless, right, times v infinity. Okay, and that's for that reason, I can multiply all, I can make every v here to be v tilde, and the only point here that in every place I have v, I should multiply it by v infinity, right? You see? And this implies that, but then it cancels except of here, because here again I have, no, I did a mistake, wait. I did a mistake. Okay. Let's start with that. Right? I'm writing for every v, it's v tilde times v infinity. No. Okay. Okay. Forward step. I told you that every v is becoming because derivative with respect to x is derivative with respect to t times v times d, right? But here also I have a derivative with respect to x, and here I have second derivative with respect to x. You see? So I have no time to spend. At the end of the day, what you have here is r, and you can throw all the constants in the problem, right? And r is what called Reynolds number, which, if I remember it correctly, is n over d times v infinity or something. I mean, you can check dimensions, right? Okay, something like that. That's the only parameter in the problem. Now, what the question is, what happened when Reynolds number is very, very large, huge? When Reynolds number is very, very large, right, what does it mean? It means that the viscosity is very, very, very strong, right? It's like not having not water here, but honey. You see? Mm-hmm. And in that case, one can solve the for the streamlines. Not one. Taylor solved for the streamlines. In the case when r goes to infinity, right? That's a very large Reynolds number, right? And what you get is, and he even found that in that case, if you have, for example, not a cylinder but a sphere, the drag force is 6 pi times ni or eta or something else that has to do with viscosity times r times something is missing here. I don't times something. Okay. This is Stokes law. If you had a lab in the first year where you threw small spheres inside the glycerin or something, that's a very large Reynolds number, and you get it. Okay. Now, I forgot. Why this? Why the fact that you can use that you have only one parameter is so important? First of all, why? Because this is a way you want to plan a new airplane. Okay, so there are two ways of doing that. One of them is to build the airplane, to enter the cockpit, to push the gas, and to see what will happen. I mean, you run on the road, and maybe you will go up, and maybe no. Okay. Instead of that, you can use the following idea: that as long as you keep the Reynolds number the same, right, you will get the same behavior. So you build one builds small version of the same airplane, same proportions, everything, but this size, right? So the D is divided by, say, 10, and then you put it in a wind tunnel, where V is 10 times higher than the speed of the airplane, and you know that the answer will be exactly the same. So you can test the proposed airplane, the aerodynamics of the proposed airplane, not in real experiments that are so expensive and dangerous, but in a wind tunnel, by extracting the fact that everything depends only on this dimensionless parameter. Okay? That's how people are building airplanes. They are doing wind tunnel experiments. Now, as I told you, when R goes to infinity, one can solve and get something is missing here. I've forgotten what. Get this Stokes law, and then the question is, what happens when R goes to R is becoming very small, right? So it turns out that when R is getting smaller, okay, for R equals 0, this equation is solvable. This is what's called potential flow, right? In the field of hydrodynamics, taking R to be 0 is a potential flow. So for example, if you have an airplane, you can say, well, okay, it's moving in the air, but what is the viscosity of the air? Very small. So let's pretend there is no viscosity for the air and say we have a potential flow, right? However, when you do an experiment and you start taking the Reynolds number to be smaller and smaller, unfortunately, I think that this is 1 over the Reynolds number, but anyhow. Yes, no, okay. Yes. Reynolds, sorry, this is 1 over 1. So this is, the Stokes flow is R goes to R goes to 0. Okay? Now, if now you start increasing R, R goes to 0 is a Stokes flow. Right. Okay, I forgot. But anyhow, when you start increasing R,
Wait, if R is 0, so this term diverges.
yes, exactly. So everything is controlled by this term.
So the F is irrelevant?
Yes, everything is irrelevant, but that's a Stokes solution. Now, when you, I forgot. I always forget what is the right. What is R? What is it? Z or 1 over Z? Of course, should be. I mean, anyhow, when you take R to be smaller, you start getting. You start getting turbulence, right? So you get something like that, and at the end of the day, I mean, there are huge turbulence around the, right? And the turbulence are becoming worse and worse and more and more and more chaotic as R goes to 0. Whereas, as R goes to infinity, in this, I don't know, whatever. Let me write it like this. Okay? I think it's the other way around, but, right? When you take, the point is that the limit R equals 0, either R or 1 over R, whatever it is, right? Which is a potential flow, is completely different than R goes to 0. Finite but small, like in air, right? One of them, potential flow, you get something that is not Taylor flow but very close, and the other one, you get the worst turbulence you may imagine.
The maggot problem.
Hmm?
The maggot problem.
What?
The maggot problem.
Yes, exactly. So it's exactly the maggot in the apple problem. Now it was a big issue I've learned when aviation started developing. So the Wright brothers, they built the same airplane, right? You know what year it was? First heavy in the air flight.
It was in the 1800s. So
1903. Very close. 1903.
what?
1903. Airplanes are 121 years old.
What?
121 years old.
I thought airplanes were much
What?
older than this.
Yeah.
Oh.
Yes. So at 1903, the Wilbur and Erwin, right, had the same the first airplane flight that took like 10 seconds or something, and but then people realized that something is going to change dramatically and in particular that it will be very important in warfare. So the newspaper in England, not in 1903 but in 1909, had had titles. Britain is not an island anymore, because everyone can. I mean, you can't trust your marine force in order to make sure that nobody will invade your island, because now they can come with airplanes. And so all the powers of Europe were involved in trying to
Build a better and better.
to build better and better airplane. In particular, after World War I erupted in 1914, they had some race of building new and better airplanes. And interestingly, even Einstein was involved, even though he was one of the only people in Germany that was against the war. He worked with a company that he suggested a new wing type for an airplane that was horrible actually.
Maybe on purpose.
Hmm?
Maybe on purpose.
That's a conspiracy theory. Maybe. Okay. But in any case, and the British guys have consulted a very good scientist, like I think Lord Rayleigh, and they told them, well, there is no point in building airplanes before understanding the reason why the damn thing is flying, what causes the lift force. Okay? And in order to solve for the lift force, you must know what the behavior of the air in its contact with the wing of the airplane, right? Because this is where everything is coming from.
Right.
But this is an unsolvable problem because of that, right? What's happened at the vicinity, at the boundary layer on the wing is not accessible until today. Nobody knows how to solve it, right? So there are a few, engineering guiding principles, but no solution. And in German, they had a smart guy called Brintel. No vowels. And he realized, he was an engineer, so he realized how airplanes are flying, right? What's going on there? And at the end of the day, even the British industry, because they had a mission to produce airplanes, so they did it without giving a damn on the scientists that have to solve the equations. But only after the war, the British committee or whatever authority understood that the Germans were right all the time and something like that. So it's a very interesting story.
There were also entire doctrines about warfare after planes, not scientifically, but British and German people saying now bomb civilians and all that.
That has to do with World War II. That's a different story.
But it started before.
No, in World War One, the airplanes were not good enough, you know,
Cross
to
the
pick
channel.
up a bomb of 1 ton and throw it in.
There was some tactical bombing in the field of battle, but the bombs were mostly hand grenades. There was
Yes. It was like, you know, taking your hand out of the window of the cockpit and
it's like throwing the stones.
throwing
from
a
a
grenade
hill.
on the enemy, something like that. This they have, but not.
Are you
not
sure that R is V divided by V?
No, you have to check the dimensions, right? From this equation, you can see what the dimensionalities are, and something like that. Wait, okay, fine. Why did I spend so much time on that? Just to try to motivate motivate you to deal with the boundary layers. And okay, so we can do, okay, so let's, how much time do we have? Okay. So there are even worse cases. For example, okay, no, I will not give you the example now. Instead, I will rush to deal more systematically with boundary layers. So this is our next topic. I will spend the next lecture also on this topic, boundary layers. But for the moment, let's speak about, right, in a more ordered manner. And to begin with, let me take also a solvable case. So now we are taking a solvable case, but we want to solve it using boundary layers, boundary layer theory. And so I'm writing the following equation: epsilon y double prime plus 1 plus epsilon y prime plus y equals 0, where y of 0 is 0 and y of 1 is 1. Okay? First of all, let's solve the problem because we don't need the boundary layer theory. I mean, I just give it as an example. So how do I solve it? Again, I'm plugging y. I have the guess y equals e to the alpha x because this is a linear equation without with constant coefficient. And what I will get is epsilon alpha squared plus 1 plus epsilon alpha plus 1 equals 0. Okay, so this is a quadratic equation. So what will be alpha? Alpha will be minus 1 plus epsilon over 2 plus over 2 epsilon, sorry, plus my, okay, so everything is over 2 epsilon. Plus minus the square root of 1 plus alpha squared minus 4 alpha. 4 epsilon, sorry. 1 plus epsilon squared minus 4 epsilon. Okay? 1 plus epsilon squared minus 4 epsilon. Now, this is 1 minus epsilon squared, you see. Right? So what I have here is minus 1 plus epsilon plus minus 1 minus epsilon divided by 2 epsilon. Okay? So if I am taking the plus, then I have minus 1 plus minus 1 minus epsilon plus 1 minus epsilon. So it's minus 2 epsilon divided by 2 epsilon. So it will be 1. Minus 1, sorry. Minus 1. And the other solution, if I'm taking the minus, I have minus 1 minus epsilon minus 1
plus epsilon.
plus epsilon, so it will be minus 2 over epsilon, so it's minus 1 over epsilon. These are the two solutions. So the general solution for y is a e to the minus x plus b e to the minus x over epsilon. Okay? And now I have to satisfy the boundary conditions. So to satisfy the boundary conditions at 0, I am saying that b equals minus a. So you can see immediately that it's e to the minus x minus e to the minus x over epsilon divided by e to the minus 1 minus e to the minus 1 over epsilon. Please check that it satisfies both boundary conditions. Okay. Now, how? So if I'm plotting now y as a function of x, I know that it is equal to 1 when x is 1, and it is equal to 0 when x is 0.
It will look the same.
What?
It will look the same.
The same as what? As this?
This.
No. Why not? Because look what's happened. When x, as long as x is much larger than epsilon, as epsilon, assume epsilon small, right? As long as x is much larger than epsilon, if x is much larger than epsilon, then what I have here, I can neglect this one and that one, right? And what I will have is e to the 1 minus x, right? Now, how this looks like, it started at e, and it goes down to 1, at x equals 1.
If x is much bigger than epsilon, shouldn't it be the other way around?
Sorry, if x is much, yes, if x is much bigger than epsilon, then I have here e to the minus infinity.
Ah, okay.
Maybe I should write x fixed if x is kept fixed and epsilon goes to 0. This is more, it's the same condition, but now it's more transparent, right? So this term and this term will go away, and I will have e to the 1 minus x. E to the 1 minus x looks like that. It started at e, and when x equals 1, it is 1.
Yeah, but it also doesn't.
Okay, now what's happened when epsilon is, say, 0.1? If epsilon is 0.1, then as long as x is much larger than 0.1, I still have the same behavior. Okay? So for epsilon 0.1, if this is 0.1, say, I will get something like that, and whoop, it will go. And what will happen when epsilon, if I have epsilon 0.01, I will get something like that, and whoop, right? The smaller is the epsilon, the smaller is the boundary layer. Okay? Fine. So again, this is an exact solution, no tricks, no shticks. Now we want to analyze the same equation as if we don't know the exact solution by techniques of boundary layer theory. Okay, and I'm going to present to you now, despite the, maybe this is something that should be presented in the first stages of the lecture, but okay, next time I will say it again. Very, very, very important technique called asymptotic matching. So what we are going to do now? Now we are saying, let's divide this region, let's divide everything into two regions. One region is a region where I can take epsilon to 0 without having any problem. Okay? This region I will call the outer region. Okay? Now, what happened in this region? In this region, I cannot take epsilon to 0 because in this region, x is comparable with epsilon. Right? In this region, x is comparable with epsilon, so I cannot take epsilon to 0 and keep x fixed. Right? This is the region that I call the inner region. And now what I'm going to do is to solve the problem separately in the outer region and in the inner region. Okay, let's do that. First, we start in the outer. Why we are doing that? Because in the outer region it's very easy. In the outer region, all I have to do is to take epsilon to 0. That's it. Take epsilon to 0, right? So in the outer region, my equation is y tag plus y is equal to 0.
To the minus x.
What?
Just
To the minus x.
Good. So what is y? Y is a e to the minus x multiplied by some constant. How I am going to determine this constant?
We have y1 is equal to 1.
Why I am taking y1 equals to 1 and not y0 is equal to 0?
Because it's on the outer.
Thank you very much. You see, I'm not using this solution because this solution is this boundary, because this boundary is in the inner solution and not in the outer solution. Okay, so I'm using only the outer. In the outer solution, I have only yf1 equals to 1, and to do that, I must a to be e. So y outer solution, the outer solution is e to the 1 minus x, which is exactly what we got there. You see? That's the outer solution. Now, what will be the inner solution? So in the inner solution, I am doing something like, you remember what I did before. I defined y that will be order 1. I mean, x diverges like epsilon to the minus 2/3. So we define y as x times e to the epsilon to the 2/3, and then y is order 1, right? As epsilon goes to 0. Here, I would like, since I know that x is going like epsilon as epsilon goes to 0. I mean, not that x, that the boundary, at the boundary x is very small. X is of order epsilon. So I will define x tilde as x over epsilon. So when x goes to 0 like epsilon, x tilde is order 1. And now I want to write this equation, but I know now that d dx is d dx tilde, dx tilde dx, which is 1 over epsilon. Okay? You see? So now I'm going to write this equation again, but for not for y as a function of x, but for y tilde, which is a function of x tilde. Okay? Or y. Y as a function of x tilde. So what we have is epsilon divided by epsilon squared y double prime plus 1 plus epsilon times 1 over epsilon y prime plus y equals to 0. You see? Okay. So so I have something that goes like 1 over epsilon here and here, and all the others are going like, okay, so I will multiply everything here by epsilon. And after multiplying it by epsilon, I will have y double prime plus y prime, which is 1 over epsilon times epsilon, plus epsilon y prime plus epsilon y equals to 0. This is the inner equation. And now I can take epsilon to 0, because now I have a regular perturbation theory in epsilon. I can take epsilon to 0, and I will find that in the inner solution I have the equation y double prime plus y prime equal to 0. Good. What's the solution for this equation?
I'll say it.
We can do the same trick. We can write it alpha squared plus alpha is 0, right? If y is equals alpha x.
Either a constant or a constant.
Note that this is not alpha x, it's alpha x tilde. Okay? So alpha is either 0 or minus 1. You agree with me?
Yes.
So y is, let's say, b e to the b plus c e to the minus x tilde.
Just x over x.
X tilde, where x tilde is x over epsilon. So this is the inner solution. Now, how do I define the, okay, so I solved here, I solved here. However, I have to match the boundary condition. So I match the outer boundary condition here, but what about the inner boundary condition?
You have a condition
I have
y epsilon.
the inner boundary condition is only that y at 0. Note that if x is 0, x tilde is also 0, right? Y of 0 has to be 0.
But you have another condition that the inner and outer agree on epsilon. Shouldn't?
Wait. So if after, so this will be 0 at 0 if y inner is b times 1 minus e to the minus x tilde. And now I can even return to x tilde of being 1 over x. Okay? So this is the inner solution. This is the outer solution. The problem is the outer, because I dropped the second derivative, was the first order equation. And after plugging the boundary condition, I have something without constants. This one is the second order equation, the inner. And even after plugging the boundary condition, I have b. So now the question is, how do I decide what b is?
You can say that the y outer and y inner agree on epsilon, and then you can find it.
Okay, so you have to do that's right, but this is that, and so this is the technique of asymptotic matching. Perhaps the worst problem of Bender's book, which is, a holy book, and the books that have the maximum amount of information per page, I think, is that they explain the asymptotic matching first in a very non-generic situation, and then they only refer you to that. So what we are doing in asymptotic matching, we want y inner at x tilde goes to infinity. Now, what does it mean x tilde goes to infinity?
Epsilon goes to
X much larger than epsilon, right? To become equal to y outer at x goes to 0. That's asymptotic matching, right? And the point is that this, unlike, okay, first of all, I have no time to explain more about that, so I will analyze it better next week, hopefully. Next week?
Next week there is
No lecture next week?
Maybe
No.
there is Hanukkah.
It's Hanukkah.
Hanukkah, it's
First night of Hanukkah.
I think the vacation is only on Sunday
No.
and Monday.
No,
There is lecture
no,
next
but
week.
you
No. After 4
finish
o'clock.
learning after 4.
No,
Yes.
I'm not sure.
Oh,
I'm
really?
not thinking.
Yeah.
It's
The
the
rest-
day
First-
before the.
No.
It's day before the first evening of Hanukkah. I
Yes.
think.
The day before.
yes.
First
Right.
candle lighting is Thursday night.
No, better.
Yes.
No.
Your first candle
It's all
is
just lecture.
Wednesday night.
It's all
You need to
the
check.
lecture.
Nearly Sunday.
Because 26th of December it's first day, but we have lectures on Wednesdays. So
Wait. On
I
the
think-
last day of Hanukkah, you don't light any candles.
What is the
נר ראשון
There is
של
a
חנוכה,
קפה
lecture
כסלו.
next week.
נר ראשון של חנוכה זה ביום רביעי, 25
אז זה אומר
לדצמבר.
שאין הרצאה.
אז זה לא יהיה הרצאה אני חושב.
שבועיים.
למה?
בימים
אתה מסיים-
בימים של
אתה
הדלקת
מסיים
נרות.
ב-4?
For 2 weeks. Oh no. Okay.
No.
Okay. So whatever. I will tell you. Okay.
We'll see.
I will analyze it much better next lecture whenever it will
Actually, you're right. It is for 2
be.
weeks.
What?
It is for 2 weeks because you have 2 candles left.
No, but there is no point in the 8th day. You don't need it. No, you are wrong. I think. I
The
think you
last
are
day
wrong.
of Hanukkah, the last day of Hanukkah is the 2nd of January, and
What
so
day it is?
It's first day.
So you,
Ah.
so you do
Wow.
light the candle next day.
Wow. Wow.
You are out of luck.
No, I always say that Hanukkah is a decent holiday if you are living in Australia. Okay. So this will happen. So what happens when x tilde goes to infinity? I mean x much larger than epsilon, right? Then this term is going to 0. So here it will go to b, and y out at x equals 0 is going to e. So b must be equal to e. So y in is e times 1 minus e to the minus x over epsilon. Y out is e to the 1 minus x. And something that you can do, you can ask for a y uniform approximation. Uniform approximation, I'm just telling you the rules, is y in plus y out minus this constant, minus e. Right, so you get e to the 1 minus x plus e minus e to the 1 minus x over epsilon minus e. So this e cancelled. And what we got for the uniform approximation is y uniform is e to the 1 minus x minus e to the 1 minus x over epsilon. Now, note that this uniform approximation, if I'm putting x equals 0, is actually 0. So it satisfies the inner boundary condition, but it misses the outer boundary condition. If I'm taking x to be 1, this is 1 minus 1, it's 1, right? So at x goes to 1, it gives me 1 minus e to the minus 1 over epsilon. Okay, I have also times e, right? But this is very small when epsilon is going to 0. This is exponentially small as epsilon goes to 0. So it's not the uniform solution. The uniform approximation does not satisfy exactly the boundary condition, the outer boundary condition, but it's very close. Okay, so unfortunately, I wanted to do much more, but this is what time allows, and I am afraid that we are going to have now a break of 3 weeks. But
We can do the candlelight here. Why not?
what?
We can do the candlelight here.
Oh, you should do it in
ואז
your home.
אחד הדתיים יחזרו הביתה.
Uh,
לא, זה חג שמותר חשמל.
זה חג שמותר חשמל. כן.
8 ימים אין חשמל?
8 ימים אין חשמל, ואין עוד דבר כזה.
אוקיי.
או בכל המועד של פסח ויתר.
אז מה רציתי להגיד? טוב, אז ניפגש כשניפגש. אתה בטוח ש... איכשהו נראה לי משהו פישי עם ההדלקת נרות הזאת? אבל
לא,
אני
האמת
אבדוק.
אני לא יודע. יכול להיות
אני
שיש
אבדוק.
לא מסתלבט.
אפשר לבדוק בלוח.
בימים שהדלקת נרות אמור להיגמר ב4 לפי
כן.
מה
אפשר
זהו,
לבדוק בלוח שנה.
אוקיי, בסדר, נראה
שאמרו.
מה...
אפשר להקדים את ההרצאות
זה
אולי.
אומר שפלטפורמה לפני.
להקדים את ההרצאות, בטוח יהיה מישהו זה לא נוח לו, אבל אוקיי, אולי ננסה. אני אשלח לכם מייל אם אני אראה. אני צריך לספור עכשיו, הייתי כל הזמן בהרגשה שאני עם הזמן בענק, לא קלטתי את הברוך הזה. אני לא בטוח שהאוניברסיטה סופרת את זה, כי זה רק אחרי 4. אז טוב, אולי באמת אני צריך להוסיף הרצאה איפשהו. בסדר.
יש לך
נפגש מתי
שעה.
שניפגש.
Thank you.
אפשר למצוא אולי...
I will give some introduction to the introduction of what I will do today. Yesterday at 10:30 at the night, right, PM. Snab tell me, okay, switch, don't do another perturbation theory. I'm switching between WKB and boundary layers that I assume you did, right?
We
Boundary
started
layers, we
today it
started
was.
to talking.
You start to talk about, that's okay.
Asymptotic matching.
Yeah, and before that you did perturbation theory? Okay,
Basic.
nice. So what I start to do is write in a question and then I find out that it's too simple for a tutorial, so I gave it in homework. Don't be scared. It is... Who knows about the correction from GR of Mercury? Everyone knows?
I didn't do GR.
No, it's
No,
more-
it's just...
It's more history than...
it's more history.
Ah,
yes.
right. Yeah, I know.
The correction from GR, one of GR tests, the test in Einstein general relativity theory, is that Mercury orbit the sun,
Perception.
but there is some precision,
It's called perception, I think.
not precision. Perihelia, there is also something like that that is the same thing as that, perihelia of Mercury. And classically, two-body problem. What do you know?
Center of mass.
The orbit is just ellipse.
Yes.
For assuming difference of mass, that one is practically its own point. Yeah. That one of the masses is much bigger than the other mass. So practically, because of a term that in order of 1 over r to the third power, there is some precision because it's add to the energy equation and all of those stuff. And I start to do the perturbation theory, and then I found out that it is actually equation that we already dealt with after substituting some variable to get nicer equations that I already did last tutorial. So that is just a hint, so you will not kill me because I told you here that you're supposed to get something that we got similar, not exactly, but similar thing to things that we already got after doing the instructions and substituting variables. So don't be scared. The question will be something like that. I will give you a Lagrangian. You're already a graduate student, you know how to deal with Lagrangian. Use Euler-Lagrange equation. Find the conserved quantities. I will probably ask you, say what is the conserved quantities that you can from each equation, and then give me, I don't know, I'm sorry, give me the final equation that's supposed to look like that, so you will have a goal to what you are supposed to, what?
So,
What?
to solve?
Yeah, no, I mean by what you're supposed to get by the end. So if you can't get that for some reason of calculation mistake and you don't care about a couple of points, you will be able to continue. That is not the point of the problem. And then it's just regular perturbation theory and find a nice precision. I think that is a cool conclusion.
We're just discussing right now the next homework, right?
That will be the close homework. You were actually supposed to get that last week, and I was supposed to I was supposed to upload the homework with that last week, but then Schnell told me that I'm a little bit ahead of him because I finished perturbation theory, and then I slowed down and asked him what he will do next lecture. We just in contact, and then things change, and luckily for you guys, I didn't thought I will finish perturbation theory and I will continue it today. We will continue a little bit of perturbation theory, and that's why you didn't got the homework last week.
So we'll get to it.
So you will get today, and it will be shorter because don't want to give you heavy homework, because next week we will really get deep into boundary layers. That is something that appear in practice.
Next week that might not be a lecture.
Okay, so next time, I will say it like that, we will really get deep into boundary layer. Today I just want to set the mathematical background for boundary layers and all of those stuff, and do nice perturbation theory problem. So it will be chill. It will not be and you will not get a very complicated homework. You will get something like 5 questions. Originally it were supposed to be 3, but then we had a longer time to discuss on perturbation theory, and Schnell really liked to ask that in tests, so it's good. So let's start. What I will do today, I don't know if you know, but I really like oceanic physics. That is one of the topics that I like, and in research is closely related to that, but not exactly. So I brought an example from practically oceanic physics, and we will do perturbation theory. So let's start. So there is a lot of explanation about the equation and a lot of, I will call that unnecessary stuff in the tutorial. It's just background for someone that don't have the background and don't want for some reason to watch the records, so we will be able to just read and understand. I will present most of the necessary background, what I think is essential for understanding the problem. Practically, we will have equation that we'll first write the equation that look like that. That is common phase, right? All the semester we looked on equations that look like that. So
What is that?
I will define everything, don't worry.
It's plus or minus?
But what? Plus.
Or minus?
There's plus. Just look on how it looks like. you're familiar with equation that's in the form of y2 primes f of x y, right? Just that for now. That's why I thought on giving that problem, but it has some spatial essence that I'm sure Oz will really like, because he really like Math of Physicists 3. We actually do nice stuff here to solve it. It's a little bit different orientation of looking on that ODE. So let's say what this equation actually means. Okay? So practically phi, okay, maybe we should start from saying what is the equation that describes the physics of oceans. Someone know? We already discussed on those
Wave equation?
Wave equations, but be more specific. Navier-Stokes. Exactly, Navier-Stokes, PDEs. If you can solve that, contact me and I will publish the paper with you and we can split the $1 million. Not worth it. If you have the solution, just publish it. Okay, so what you're doing usually in Navier-Stokes is finding a solution. Let's say we have variable A. We finding some zeroth order solution to Navier-Stokes that can be solution at equilibrium, at steady state, not exactly the same. Okay, solution that not depend on time, something like that. And then you add a perturbation from that. Perturbation, usually we will denote that by delta A. And then all things that in order of delta A squared, you just throw away out of the equation, linearize, and then you're supposed to get the solution.
Delta A squared or
The
delta squared
first correction, right.
Delta A squared or delta squared A?
What you will throw away is O of delta A squared. And usually it's common to assume that all perturbations are in the same order, but sometimes you will actually want to break that and assuming that the perturbation in different order, because the effect you will want to look on is coming from different perturbation, that perturbation is only contributing, that most contribution coming from that perturbation. Specific perturbation, let's say velocity, perturbation on velocity. Sometimes if you have a very slow flow of water and you want to find a perturbation that is practically near zero, you want to weighted the perturbation to be, you assume that actually, to be much bigger than the density, for example, perturbation. So that is just the background to say, I wrote that also in the tutorial, the perturbation on W, I forgot the name of that, the velocity in the Z direction, our system is ocean and we look on that as flat ocean, that is the Z, X, and actually we have also time, how it's developed with time. Just looking on the profile of the ocean. Here we have ocean, and here the wave are changing with time. See the picture? So W is the velocity in Z, and I'm practically assuming that there is phi, some sort of a place function that satisfies that condition. So what I'm practically saying is you can't integrate on W the velocity. If you want, if it's confusing you the delta, just look at that is the velocity in the z direction, vz. Okay? And what I'm looking here, it's practically zero on average, right? The perturbation in z. We assume it's near steady or something like that. Okay? So practically that is vz. And we want to define some sort of a profile height to the water, right? That has a spatial name that doesn't, we don't care about that in our case. But it's practically saying there is, phi is the integral on time of w, but it's not exactly that, right? That is partial derivative. It makes sense to define phi because it has the feeling of a position function, right? But it's more like a height function, like if you have a string, right? String that attached both sides to a wall, and then you have the function psi that is the height of the string at each point. That is practically the function of the string. But here, if you want to look at that, you have also here phi defined. So it's not actually the, I will call that the height, because phi is function, w is the velocity in z, right? You don't expect the velocity in z to, in z to not be, to be zero or something like that here, right? So what it really is some sort of how will you call that? Magnitude of the string function is I think the best way to think about that. That is something that presents how fast the okay, maybe I'm trying to give intuition without using advanced stuff, but it's practically simplify your life and equations, so you can look on that like that. But think about that when the velocity is very high, and practically phi is omega times t because integrating on t, roughly. So phi, let's just say for our intuition, be omega t. It is practically what is the distance that you will do in each point. That is the intuition. And to which direction. I think that is the best I can do at, yeah. Actually, the direction we know, it's the z function. It's how far you will get in delta t time. Why? Because phi, you can look on that like w times t. It's just the distance. The distance you will do in a delta t seconds in the t time. So it's some sort of a height function, and as a cause of looking like that, we have some boundary conditions. What are they? We have, let's draw our system here. Here is the z direction, here is the x direction, here we have the water that is roughly at height h. Okay? On average. Don't care. You don't see here any waves. For me it's flat. Okay? And here it's z equal to 0. So what will be, if you think about phi, what is the distance that you will do in very short time ahead? What do you think is the right boundary conditions on phi? in H and in
z equals 0.
yeah. Let's write it with z equal H and z equal to 0. So here it makes sense because you are not expecting to move a lot at the boundary because of boundary effects, right? Okay, for first order you can maybe take a correction, but I assume that on all orders because I want that to behave like that, and you can use all Zumwelfeld that we presented a long time before to find what happened at the edges, and you need to make sure that all the conditions for that is valid, but okay. And at H, because of due to gravity, you're not expecting it to move a lot also, right? And we assume that we know that water is incompressible. We are not expecting a lot of mixing unless there is, we study in waves, Kelvin-Helmholtz instability. If you remember that when you have two mediums, different mediums with different wave speed in them, and they are interacting with each other. A little bit on on gravity waves in the wave course, if someone remember, but it's not essential. So that is our boundary condition. So everyone understand what phi present? So now just from linearization of the equation, we get that nz, but I should probably also write what is nz. We'll not give intuition on that. Assume that is just function that comes off from the perturbation theory. You end up with that thing. Okay, I'm already giving you the perturb equation that we will do perturbation on it. Okay. I'm just searching.
So you got this equation from Navier-Stokes?
Navier-Stokes, doing perturbation on Navier-Stokes with my assumption. They roll
And
them.
then you get.
You get that equation.
Okay.
W is actually nicer to work than W because a lot of things cancel out. You assume that everything is a wave that moves in the x direction. So practically all quantities are times e to the I k x minus omega t. Also here, e to the minus k x minus omega t. That means they move only in the x direction and they are a function of z. Okay? You understand why I'm assuming that on the perturbation? Just, you can think about that as a Fourier transform. That is just how one mode develops. If you know how one mode develops, you know how it will behave in delta t time. Right? Reasonable for everyone? Yes? For you also? If you have questions, feel free to ask. So, now just the final thing
What
is
is A? Big A. It's like what? It's phi or.
it's just general
Yeah, but
quantity.
in our case.
In our case,
Yes.
it's phi.
Phi?
Yeah,
Okay.
it's our phi of z. Let's call it like that. I assume here that phi is function only on z because I told you already it satisfies that form.
It's a general function, right?
General function that depends only on z.
But the derivative should be 0 in this case.
Derivative with respect to what?
To t.
To t?
Yes.
Okay. What I mean, it's different because here I mean the velocity and how I actually have to write it like that, kx minus omega t,
Oh, okay.
and here,
Yeah.
so I k.
You mean the dependence on time only in the exponent?
Yes.
Okay. function
It's-
is only.
Yeah, it's half assumption. It's practically looking on one mode from Fourier transformation. If you know how it will behave generally, you know how you should sum all the waves in the Fourier. You will find a constraint from our equation, and then you're free to go. Practically, you know how the system will behave. And I'm just searching where I wrote what is n. I think I wrote that only in the appendix.
Oh, I saw it in the original
No, here.
statement.
Maybe. But I wrote the appendix not long ago, and that thing I wrote in the something like the question itself I wrote a couple of days ago. So yeah.
And row 0, what it is?
And row 0.
Yeah.
Row 0 I explained here. I'm taking in all quantities the 0th order. It's just, I'm assuming it's near steady state. So it's the density of steady state equilibrium of the system.
Okay.
And that is given to us. Practically, we assume that this thing is given. G is the constant from gravity, and I should also say what is C. C is just omega over K.
Where is the perturbation?
So this is the speed of light.
What?
Where is the perturbation?
Wait, I will say what is the problem, and then I will I'm just introducing the system.
Vz equals to omega eikx or minus omega t, or it's W?
What?
You wrote there Vz, I'm not sure which letter you wrote there.
Vz is equal to the
The
velocity in the z direction.
No,
Yes.
I understand what's Vz. I don't understand what is the letter after Vz.
W.
W e to the I kx minus omega t. Okay, so that is the system. You get that from perturbation. You can read what I wrote in the tutorial afterwards. For now, I will just write how it can appear in tests. Sometimes in Schnell test, he give you the background and all of those stuff, and he asks you the first question: what is the constraints of the system? So you will have to write that, and that is approximately 5 points. And then the next question is: here is a equation that arrived for Navier-Stokes. Now solve that. And our question will be exactly: you have that thing and this given function. Okay, it doesn't matter what it means. I wrote here so you can have some intuition about that. Physical intuition, I think it's nice. And now, oh, by the way, that is negative. When you're getting up, it's lower and lower mass because of gravity. You know that it will be more and more dense here, and here it will just be less and less dense. So the derivative with respect to z will be negative. That's why I have the minus sign here to make that positive. Okay? Yeah. That is also. And now what I'm saying is we assume that n squared is near a maxima. Okay? Assume that n squared near a maxima, let's call it n0. Okay? N squared near okay. So what I mean, it's not fluctuating a lot from that value. The fluctuation is small. Practically, the constraint I'm putting here is, let's call n0 to be the maximum. I'm assuming that nz squared is much less
Then 1.
than n0 squared. That is what I assume. Okay? So now I can actually rewrite n. Question?
For any z or near?
For any z, for all z. Okay? That is the mathematical way of writing for
Yeah,
all.
Yeah, but
Okay.
what is if we're close to the maximum point? This is wrong. I mean, no,
I mean the
so- so
maximal
from-
value, near the max value.
You have
So
you have some z.
I'm assuming that we're not fluctuating a lot from the maximum. You can look at that as that is the maximal point, but it's also the average, I assume. But it may be better to look on that as an average. That will be also valid to look on that one as an average, and it will be fine. Okay? So now what I'm doing is I will write the system with small variable. I will write nz squared. We need to do perturbation theory. In order to solve that equation with perturbation, we need to define a small value, right? So we need to, I assume you already did that with Snap. You sometimes introduced a small variable epsilon equal to 1 actually. You did that with Snap to the system just to make sure that you know that something is very small. You can afterwards even substitute value for epsilon and normalize it like you want. So how I will take that, and I think most of the time, okay, not most of the time, but it's a very nice way to do it, is I did it with minus or plus. Just a second. Okay, I did it with plus epsilon gz, when gz is actually that thing divided by that. Okay? It's just, you can think about how that's called from labs, relative error from the average. Okay? For me, it's reasonable to define epsilon like that when that is the constraint. Okay? I think in something like in 2014, I think Snirb gave in test something like that. He gave something that looked like a relative error, and you will need to do something like that in order to find the perturbation. It practically told you that. Now define a small quantity. So epsilon is practically equal to 1, but we will erase that because gz is general. We can define gz to be even with some constant multiplication that will put gz in order of 1, right? And then all the constants we can put in the epsilon, just make sure that they're small. Okay, so, and now the question is, do find phi and c the speed of waves in the ocean to order of epsilon. Okay? is the question clear to everyone? What you practically need to know of those stuff were just introduction to and presentation of the system. Now you can just look on that equation, look on that, look, epsilon is very small number, okay? And just say, okay, now we want to find C2 order of epsilon. C is also a function of how close we are to be practically constant, because it's how waves propagate in the medium. In this case, in the water. So is it clear? Can I start solving the question? I was clear enough, or someone lost me? Okay. Dima? Okay.
This will be key for us, or I mean this.
Sometimes what I thought to do is actually giving you in homeworks with nice details. Practically what I'm doing, if I'm not sure if what I wrote is clear, I'm asking Kalimsky to correct me. So I'm practically, you will have instruction of how to write the equation. You don't have to derive that equation, but to write relations like that, you should know. But there are infinitely many options to do that, and if you have nice idea, it will be also accepted in the test. We are physicists, we don't want to fail you because of irrelevant stuff. We just want to check your understanding.
Irrelevant stuff like math.
We will not fail you on math, but if, for example, you did asymptotics wrong, that is a problem. If the epsilon you introduced now contradicts the asymptotics, it's bad. If it's not catching the asymptotics you do, it's bad. That's what you need to practically do. So let's now solve the equation. What we actually assume is phi. You do it perturbation theory. We want to find that in order of epsilon. So we have phi 0 as a solution, the 0th order. A solution to the perturbation equation, to the perturb equation. That we solve that with perturbation theory, because in fluid dynamics in general, it's very complicated, and most of the cases you can't do that. Actually in 2D it's much easier. That's why I'm looking only on the profile, because in 3D you have some very strange turbulentic that can occur and all of those stuff, and the equations will be nasty. If you're interested in that, I can show you very messy equations. What? And now, also on C, the speed in the medium, we will use. C is practically constant, but that constant is depending on epsilon. Okay? There is a dependence in epsilon, because practically the density that is represented by m, the effect of the 0th order density, is clearly affecting the speed of the perturbation. So you have to take, in that case, also a perturbation on the speed of waves. That is actually a question that sometimes appears. What will be the perturbed quantities? You need to understand the physical system, then explain in short sentence why it's perturbed. Practically n is related to the density, right? if you're doing perturbation that relates to n, we are perturbing the density, and we should expect the speed of waves to also perturb because of that. And the function of phi we should also expect to be perturbed by that, right? So now after we wrote everything, just neglect everything that in order of epsilon squared. Easy as that, just plug everything in and neglect all the things that is in order of epsilon squared. And what you should get is the in very short time, Oz will understand why I said he will really like that, and why it will be math for physicists 3. You can practically think of that as eigenvalue problem. It's some sort of, I don't want to say unnecessary words. You know, the speaker in the seminar said something about Sturm Liouville, and Ruchman were in the room, and he was the one that taught us Sturm Liouville, and he gave to me and Kalinsky a mean look. Do you know that, right? I gave him thumbs up with a smile. Yeah, I know what is Sturm Liouville. Yeah, so it's very funny. So, and if you want me to plug it in and show you all the unnecessary calculations, I can do.
We believe you.
That is bad. And now that is the messy
Why phi 1 is squared?
What?
Why phi 1 is squared?
Where phi 1 is
Phi
squared?
1. You wrote phi 1 and
It's
it's
the
Oh.
second derivative. Ah,
it shouldn't be
Yeah. It should not. I don't know why I wrote it with squared. Actually, all of those equations, after a little bit of practice, you can just plug it in your head and do that and sum all the terms. I think that's what they did, and then gave to ChatGPT what they did and asked him show all necessary steps, and he just wrote it very nicely with explanations. It's right, I checked, so should not find problems with what he did. But to type all the steps between to get to that is a little bit of a pain, especially if you do it in orderless, it will be a pain. So what is the zeroth order solution?
you look when epsilon is 0.
Right, just set that to 0, and what is that? Harmonic oscillations. Why I said that n0 is practically maxima? Because moving it to other side, moving that to the other side that has the form of Schrödinger equation with a potential n, and you want to find the minimization of that, right? You want to minimize the potential. It has a minus sign, so, right? See that? That is very cool. So that is also an intuition to that. So why we get that oscillatory, because n0 is actually a maxima that affect like a minimize the potential. Yes?
Yes.
Tamar?
כן.
Ken? So the solution is in the form of a sign. Actually, if I'm saving the sign, you will understand very short, or you will already, yeah, because of the boundary. That is what's left, and amplitude is nicer to stack with a than stack with other stuff. Actually, I think, okay, we look in the short. Did I wrote the amplitude in my solution? Wait. Yeah, I will find. So that is what we found out. And actually, from our constraints, what we get, that phi 0 for 0 we get equal to b, but that's supposed to equal to 0. Therefore, phi 0 is just what? A sine and 0. Okay.
Yeah.
And now let's get the other constraint. Just plug in z equal to h, and that is practically quantifies our equation. We have discrete amount of mode that are valid for our equation. I write that the nth mode, 0th order of the nth mode of the speed of sound is I n, and then we find that n h. Quick check. Is our velocity exploding? The answer is no. It's bounded, and that makes sense, right? If that will be linear in n, that is very problematic. We can have water that just the speed of particles in them will be too fast. But now it's bounded by what? N0 h divided by pi.
And goes.
That is actually an insight of a system. What is
Wait, n starts with 1?
what?
N starts with 1 because if n0 is c0 is
What is
exploding,
0?
right?
How that can be 0?
If n.
not
No,
not
but it's-
n0,
it's,
n
It's-
small.
No, but,
solution it is zero.
Of course it cannot be 0. Yes, you are-
n cannot be 0.
any zero is a solution.
יש n 0 כפול h לחלק ל-c, הכל מספרים.
And n is a natural number. If you like, you can also say that it's integer number, but then just get 0 out of the possibilities. Why it can be also negative?
It's the same, it's just the direction.
Yes, exactly. But that is the fastest way that you can see in oceans is in the form of n0 h divided by pi. How do you get n0? From taking the maximum of that thing. That is very cool in my opinion. In my
It's when you
opinion.
can bound the maximum velocity.
What?
It's when you can bound the maximum velocity.
Yes.
Because when n is great, n is larger, literally
It
larger,
gets smaller
it
and
gets
smaller. Yes, exactly. And now we find exactly what is our function. it can be in a lot of possibilities for amplitude, but is standing wave in Z and the wave that propagates in standing wave in Z that has some nodes, right? Even nodes, that is very cool. That's why if you have been in deep sea, you saw waves that practically just get up and down, right? Exactly. In first order, it's just zero, but the next order, we should expect it to break that. That's what we expected. And that is very cool. That is how all of those big mass of water, gigantic mass of water, just move in the ocean. Okay, so now, after we did that, let's now find we find phi 0. Okay, so we actually finished. We need to find out the first correction. But look, originally, what we had second order differential equation. How many solutions can be for a second order differential equation? 2. How many we find?
1. No, not 1.
Infinite number of solutions. What do you need for that? You need the constraint of what is phi at time 0, right? And then you just find all the amplitudes, because there is still one unknown that actually the general way of writing phi now is sum of an sinus
It's
some
pi
kn is,
pi n divided by a.
let's write that zeta n because k is already taken. Z. That's why I said our tutorial today will have the charm of Math for Physicists 3, and they said that Oz will really like that.
It's also like your favorite course, quantum mechanics.
There is too much quantum mechanics in Math for Physicists 3, if you ask
Yes,
me.
there is.
But I know who to blame for that. I will not be a tutor for Math for Physicists 3, if you ask. That is nice example that, okay, perturbation theory you don't study in Math for Physicists 3, but that is simple enough question to just the zeroth order to give in at Math for Physicists 3 in homework. Something like that. Or even tell them how to do perturbation theory in very short detail. That is not that hard in that case. Okay, so now the perturb equation is just setting that to 0. Now phi 0 is given, but what is the problem?
You don't have C1.
We don't have C1.
You have two unknown things.
Right, exactly. I have two unknown things in one equation.
Wait.
How do we deal with that thing?
What is the second unknown?
C1 and C1.
C1 and Phi1.
That's two.
Yes. And now we don't have a lot of other constraints or something like that. And we should actually expect something that will break the symmetry in C that we have, the first correction, right? We should expect something that will move all of those standing waves. They will start to shift, not just be steady, right? We should have some drift, I will call that. That is a drift velocity. They actually move at the x direction, but we should expect something that will have to do with the distribution of particles that will also have an effect on the velocity, right? If the distribution is not symmetric, right? We should expect that from denser place, particles will move to low dense places. Right.
You want to write the diffusion equation?
No. We already have the equation, right? You're mixing stuff, and that is not water and air. We're dealing with water.
Ah, yeah, it's not compressible.
Okay, so let's write the equation. Actually, solving for phi1 is very easy. I can write a general solution. What it will be? We have equations.
It's all constant,
that's
so you can just use the polynomial.
Variation method, right?
Oh, okay.
Method of variation, that is the non-homogeneous term. Easy as that, we find the solution.
Yeah.
But now we have a constant C1. How do we deal with it? That is a trick. I really like that because I took that from a test in the math department, which I had. Actually, they gave us in linear algebra some equation that involve a lot of stuff, and you had that trick, and that is practically use it in ODEs. That trick also has been in math of exercise 3. That's why I said as we like it. We will define an operator. I am represent it a little bit different than how I wrote it in the tutorial. The tutorial I wrote it not like a very big trick, but I'm presenting it as a nice trick. That is my operator. If you like, you don't understand why I'm adding constant to derivative, here it's just the identity operator. Okay? Now what I'm doing is practically looking. Someone gave you at the middle of the night an operator. What is the first thing that you're checking?
It's a unitary.
Emission, right? Exactly. And we know that derivative is anti-Hermite.
Got the key to your house.
Well, we know that derivative is anti-Hermitian, right? So taking the second derivative,
Will be
it's Hermite, and the identity is Hermite times constant Hermite. Those constants are real. If they were not real, it will be a problem, right? But luckily they are real. Right, Dima? You believe me?
Yeah,
Say no.
but I don't understand why the first derivative is not Hermitian.
First derivative?
I.
Why you multiply the momentum operator by I? To fix the Hermitian of it, right? The momentum operator, it's in the form,
but it's not
in
quantum
the I
mechanics.
direction, in the form of that.
Yeah, but
To fix the Hermitian, when you're looking on the dagger, the conjugate of that, what you will get from the minus I turns to be I, right? H bar, and to be Hermite, that means that this thing should be equal to this thing. The momentum is Hermite, so that thing should be minus the I. You can see that also with integration by parts. Actually, our function phi 0, I secretly define it to be 0 at the boundaries. That is exactly what you need for doing what I do here.
yeah, but these operators from quantum mechanics, right?
No, they're the same. That is the derivative operator. Just present it with known things that you know already. Permission of operator. Come to me after that, I will explain it. But for now, just believe me that that operator is Hermite. Okay? That is also, you can look on that as a free particle that is practically some sort of Hamiltonian. Okay? If you see that. And you know the Hamiltonian is Hermite. That, or you can do the integration by part and see why it's Hermite, because it's zero on the boundaries. Also, if you saw that, I set the boundaries to zero exactly for that case. So I can say things like that very easily without thinking. So, what is now happening, I will just multiply all the equation by phi 0 and integrate from 0 to h. Okay? So the first term is actually phi 0 L operator times phi 1 dz, right? L, our operator, is acting on phi 1. And the next integral from 0 to h gz minus 2n squared of c 0. Actually here I need phi 0 also. The third power times phi 0 dz is equal to 0. Okay? But here, the first thing we observe, that thing is only depending on phi 0. Right? Oz? You agree with me? Okay. And the second thing, what is that? That is just the inner product, right? That is phi 0 with, actually, we will write it in that form. That is just L acting on phi 1. Here we have phi 0. And that is just the inner product of our system. Actually, we need to do 1 over h, but if you want, you can just multiply it by h. Okay, I don't care. For our purpose, that is our right? Okay? So now you can just, because that is Hermite from the definition of formation, we can just move that L to the other side. So it will be phi 1, phi 0. Right? And what is that?
This is
0. Did I erase that? Or it's still here?
No,
No, left side. Okay.
Left side.
Yeah. No.
Where you wrote that?
Yes.
Here. Exactly. And now we got 0. How cool is that? Right? And now
the product.
we just have that dot product of things, and we can write in integral form. Here I'm missing C1. Is there any better marker? Okay, that is good enough. And now we can find C1. I can find C1, we know that thing, N0 squared divided by C0 squared. Wait. Okay. We have something that we can divide by n squared c0 squared, right? And here it's just like that. That we say it goes to 0. And now we have just 2 over c0 of that thing, so we can separate the integral because of linearity of integral and divide by what we need. That is practically c0 over 2 times in the numerator it is, let's say, exactly 0 to h of c0 squared dz, and the numerator it's practically the modified inner product, some sort of modification on inner product, right? And that is our solution for C1. So now after we found C1, it is very easy to write Phi1 and find him.
Phi1 will be just the non-homogeneous solution for the problem, right?
Yes.
Okay.
The homogeneous solution is practically, you can put that in the zeroth order solution.
Yeah, of course.
Because it's the same. So, and actually we can do one more simplification. For all phi, if we take, if we take only one mode of that thing, we can write phi 0 squared for only one mode. If I'm taking an initial condition of a sinus, actually didn't draw that in the tutorial, but you will understand that what matter. That thing is just h over 2. So what you get, C0 divided by h times integral from 0 to h of gz phi0 squared dz. Actually, if you will move the 1 over h to here, it's like the inner product. It's like taking some mode phi0 g phi0. Yes, that's right. That is, it's looking similar to things that have been done in QM2, right? But now in cooler areas in physics. I'm sorry, I'm biased. So it's actually very nice, in my opinion. And to find
mechanics.
what?
Quantum mechanics.
Yes. I'm showing that not all examples should need to be in.
Include H bar.
Yeah.
Yeah.
You can
I
add
like
it if
quantum
you want.
mechanics, but to some degree, it's not should be.
Yeah. I'm just burned out with quantum mechanic example in undergrad studies.
Yeah.
Because every time you have example in a test, or even in a test, they want to give you a physical system, it's always Schrödinger equation.
Yeah.
I hate that.
Why?
In all the math courses I did in the physics department.
Maybe because Schrödinger's equation
Yeah.
is so fundamental, it's simple to understand, man.
I know why they do that. That is not the question. That is
Why they do that?
because most of the physicists today do things with quantum in the name. Most of the physics. But in the
Until
past
it's in
it
the
were not
title.
like that.
Yeah,
Until it's in the title and does not interact with quantum.
even though it's in the title, it does not
So-
promise you that it's indeed quantum mechanics.
Phi 1, maybe I should call that homogeneous solution, so I'm noting that with H. That is the general expression for the homogeneous solution. And now, why I wrote it like that?
Wait, while you are interested in the homogeneous solution, I thought you
So that's a parameter.
Yes, I'm looking on what I did. Where, 1 second. That is the homogeneous solution.
It's
No, I
just
should-
the Veroxian is 1.
The Vronsky is 1.
It's always 1 in the harmonic oscillator.
Yes, you're right.
And the
Okay,
variation
and now it's just integration, so
Yeah,
No,
so
but-
I will not bother you with that. I did that very late at night, so I will need to look on what I wrote there. Probably I will erase that and just write now it's variation of parameters, do it yourself. Have fun with it. Now the last topics, just the introduction of boundary layers. So you study already with Snarb that, you start. It's practically you have ODE. Let's write that. Most of the time it will be second order ODE, but it can be whatever you like. That include epsilon, y tag, y2 primes, and actually y.
You mean whatever Schnell?
Yeah, what Schnell. That is the general expression of OD, of the OD, right?
Yeah, but epsilon should be in the highest order. I mean,
Otherwise, it won't be.
yes.
It won't be.
boundary layer.
Again?
Epsilon should be multiplied by y2 tags,
It should be in the coefficients of the highest order.
highest
Derivative or
yeah.
highest order
In other case, it won't be
order polynomial.
boundary layer.
Otherwise, it will be
Yes.
regular, just regular
Yes,
Perturbation.
okay.
perturbation theory.
Yeah.
There's no special, and then it will be this one.
That is the same thing,
Yeah.
practically.
No,
You
it-
can say that is also a function of epsilon and
Yeah.
just...
Epsilon can come in more terms. Just it must be in the
Yes.
coefficients of the highest order.
If you will open what I did in the tutorial, I wrote it in that form, exactly like you said. Okay. So here what I'm doing is practically you have two ODs, the inner solution
And,
and the outer solution. The inner solution for our case is x, y, y prime. Actually, we'll start from outer solution. Now it's in the limit of epsilon goes to 0, right?
No, it's exactly 0.
Taking the limit
the
for
out-
continuous function is the same.
Okay.
That is in the limit of epsilon is 0, not x is going to 0, and then you have the balancing.
when solving, we just neglect the terms with
Yes.
epsilon.
And that what we find out. That is practically you have OD. Now for finding the outer solution, now epsilon tends to 0. That is our new OD, and you know how to solve that.
Yes.
Nice.
Hopefully,
Dima can solve all the ODs in that form. Right?
Of course.
Dima the king for this.
With with enough courage and Python open, we can solve everything.
Numeric analytics.
So what it will be the inner solution? The inner solution, what you will do is define a small t that is x divided by delta. What is delta? The width of, yes, exactly. We did that already.
Yes.
That is the width of the solution. Told you I actually studied, yeah, okay. When I saw that, and we had homework that also include perturbation theory on solving polynomials, I use that width also, and Kessler told me it's good and nice stuff because it's making even a machine be able to solve those equations. So you do that thing. Delta is just small scale of our solution. The width, we already defined it, so now I don't need to spend time on that. And now I will denote with dots derivative with respect to t. So what we get is x equal to delta t, 6, y. Now what is y prime? We want to write that as derivative with respect to t. General.
Delta, right?
Hmm?
It's y tag multiplied by
1 over delta.
Why not?
Why?
Yes.
Because
That,
if
I know.
d, yeah, I'm just writing it. dx mapped to delta dt. So you can think about that as d, a number, divided by a number dx. That is just mapped to.
If I was a mathematician, I would kill you right now for saying a number over a
Nah.
number is derivative.
Now, depending on if you're in algebra, you will probably kill me for the notation. But people that use applicable math, they are practically worse than physicists.
And it's recorded so we can send it to them.
You know one? Give me a name of one
I'll ask the one.
applicable.
You forgot epsilon, I think.
Why did
No, it's inner solution.
Times epsilon. Okay. Equal to 0. Now just solving it for appropriate width and solving that system for linearizing in delta. So present that as g of t y y dot y 2 dots plus o of delta squared equal to 0. That o to delta squared we throw away, and that is practically summarize what we are doing in order to find approximated solution in a specific region. Right? Until now, Schnell did everything, right?
Yes.
And now, and that is just summary of how to solve that. That is nice if you have one sheet of paper that you can take on test, you can bring something like that. And the last thing that is nice to say, that okay, that what is the main goal? Doing global analysis, right? But that look like what? Local analysis. The magic is if you have, I will write that, will erase that thing. That is the magic of boundary layers. That it's look like you're doing local analysis, but you're actually doing global analysis. you have something like that. You have x, and to here, that will be the inner solution.
You should also have two boundary conditions.
What?
You should also have two boundary conditions.
Okay, what?
You should
Yeah,
also
I
have
should add two boundary conditions, but okay, that is already given to you in most of the time, or it's like a physical problem that you have to know physics in order to find it, right? And here you have outer, but what is the problem? There are also a little bit, there is not exactly a place that a point that they're stopping being valid. The outer solution is actually stretching to here. And the inner solution is stretching to here. Okay? By the way, there is no reason that the inner solution will have bigger area than the outer solution of validity. It just my dog. That it will not be at the middle or something like that. Okay? So one constraint that you get actually is your solution, actually why it's called boundary layer, because in the boundary you have another constraint that, we'll say it like that, it's a little bit of a cheat. I will write it more general than what Snarb wrote, than how Snarb wrote. It's actually, I wrote it in the tutorial better than how I wrote it in the tutorial notes, because it summarized everything and generalized. That is the Wronskian of both solutions. It's the limits of x being much bigger than delta and x being much lower than delta. They should be, actually the Wronskian should be the same, and if it's defined it should be also equal, but sometimes the limit is not defined, and then you need just to take the behavior of each function that will provide you with the right answer. If that thing for x is much larger than delta goes like e to the x.
Yeah, but the question before, you look for the out solution for the case of x much smaller than delta. But
Again, I'm sorry.
for the out you took the x to be much lower than delta in the limit. But
For the
delta-
out, I taken x to be much bigger than delta.
Here you wrote much lower.
Yes, because now,
No,
where they're
I'm
meeting, here it's the region of y out.
Yes, no, but I'm talking about this limit. You say the
Well,
limit where x is much.
How do you take
smaller
y
than-
out to be in the region of y in?
Yes,
Like
it's,
it
it's, it's a much other problem since delta is not present in the out solution. You introduce the delta parameter only for the in solution.
Okay, yes,
For
you're
the out
right,
solution, you
you're
can't
right.
talk about it. You need to talk about epsilon goes to 0. Because
Okay, I will say it like that. The constraint will come from x approaching 0.
Okay, no. X doesn't necessarily go to 0 in the out solution.
Okay,
Because
going
it
to
might
the
be
lowest
the
boundary.
In
If
the
It
order
might
of
be the
epsilon.
opposite.
what?
In the
It
order
might
of
be
epsilon.
You don't have what Kalinsky says is in the outer solution you don't have epsilon.
No, you don't have delta.
You don't have delta, you can have epsilon.
Okay,
Just
Epsilon
in the
goes
order
to
of
0.
epsilon. That is the meaning of of delta.
okay.
X is in the order of epsilon.
Yes,
Okay,
X in
so-
the order of epsilon.
So what is the problem with writing it with lower delta? It is exactly the same. I can do it with that is fine. That is that was written here. Here it's practically delta. You can look on that as the boundary. They're both the same. So here you need to take much bigger approximation. Practically, okay.
Yeah, you
in the outer.
stretch both of them to the other side.
Yeah, exactly. But you need to say compared to what, so I say it compared to delta.
Okay.
But it's practically
You
all
mean
the
outside
time.
of the
Yeah,
region.
all the time just take limit.
That's
Here you take x to infinity, and here you take x to 0. It's just formally way of writing it. So, but
If
there
it
are
doesn't-
some problems. If that is y in and y out in the limit, okay?
Yeah.
Goes like that, let's say. Out is, let's say,
You should have a constant in one of them.
what?
You should have a constant in one of them.
It should have a that be.
Okay.
In the inner, yes. If you have some boundary condition in the outer, it's already first order
Yeah.
solution. So
In
most
the
of the
inner
time,
you have it.
only in Kessler's test, we had actually inner part and matching it to the outer part. That were the point of the question. Not that hard, but I was the closest one to get all the points. Most of the students got less than 15 out of 35. That's why we had 16 factor. And I failed on the question that everyone succeeded.
As usual.
Yes, yeah, right. So, and y out is going like what?
So,
Let's say, wait, y in, we'll want it to, let's take it like that. Ln of beta x, and y out is going like ln. So in that case, actually, doing the matching is very hard. You can observe that the matching will be beta equal to 1
yeah.
and say, but you don't have the limits in each case. And a generalized version of writing it will be writing it Vronsky equal to 0, because that thing will not be valid. That's why I wrote the Vronsky equal to 0. That constraint have to be.
Another
Yeah,
question?
actually, there is a problem here, because they actually independent of, no. I'm fine.
Small question.
Yes.
The in and the out on the plotting, they're not necessarily in this order, right? You can have the out in the left side and the in the right side. It depends on the boundary conditions and how you.
Yeah, okay, if you want to
That's
solve
it.
that for minus infinity, for example, your outer
it
part,
depends on the boundary condition and the
Yes.
equation you got.
if your boundary condition is, for example, minus infinity is something, have fun. You can even define your outer solution to be until from 0 to 1, the whole system. But the
Yeah,
boundary
okay.
is not like x approaching 1. X is very big compared to what? To delta. Okay?
It's just rescaling of the system. Just as if it might be a case where out in it's approaching 0 and in
Yes.
approaching 1.
Actually, the first example, I did that. Do you want me to do it? It's very quick. I think we have time for it.
It's 1
We
minute.
have 1 minute.
It will take 5 minutes extra, if you like. If no, I will do it only next week, but it's okay.
Next time.
Next time, okay. We'll do it
I
next
think
time.
we're all exhausted.
Yes.
I think everyone agrees.
Yes.
So that is just the introduction. So next time I will not have to do that. Then I will do the 2 examples I wrote here and one physical example. I'm I will probably take something from my research because I have some case of plasma. When the plasma frequency you're doing, your epsilon is practically omega, the frequency of the plasma. And you're solving it in different regions, and then you get the uniform solution. Oh, actually, one more thing that I should probably say is your final solution is y equal to y in plus y out minus y unif. Here, for example, for that case, u unif will be ln x. Most of the time, u unif is just a constant that you take into account twice your solution. So it's just depending on the problem. I brought two problems. One, it look like that, and one is just a constant of doing that. And by the way, one more thing I like to say is what is the benefit of doing boundary layers? The benefit from doing boundary layers instead of doing perturbation theory. That is a really important thing.
Easier.
Sometimes when you're doing perturbation theory, you can get a solution that not satisfies the condition. For example, in probability, it can be non-normalizable.
Yeah, but that's why it also doesn't satisfy
That-
both the boundary condition.
yeah,
Just on the limit it satisfies it, but not exactly.
Well, again, what did you
Just
say?
give us an example
Yes.
that the uniformical solution does not satisfy the outer boundary condition, only at the limit of
It's
epsilon
only on the
goes
limit
to-
of epsilon goes to 0 or something like
It satisfies that.
that. Or x is much.
No,
Yeah, it's not-
some of the limits.
It's
Depends
not
on the
exact
boundary
solution,
Yes.
but do you mean it can satisfy the boundary condition only when epsilon equal to 0?
Yes,
Yes.
yes.
Yes. So, okay, actually we're not aware of that thing, but in most of the time if perturbation theory not work, you will go to boundary if you can. Sometimes you can't. And that should be a nice place to start.
החישובים פשוטים יותר.
Yes,
Much
it's
simpler.
much simpler calculations
theory
and
compound.
Yeah, because on one side you don't use perturbation theory, on the other side you use perturbation theory of a much easier question.
חוק שימור הקושי.
exactly.
מי כתב את החוק הזה?
חוק שימור הקושי, זה
שנרב.
חוק שאומר שקושי
Your
מופיע בכל
lecturer.
שאלה שאתה פותר.
זה נכון, זה נכון. אבל לא בכל התחומים, בתחומים ספציפיים אבל.
בכל דבר.
לא, הוא לא מופיע
אפילו אתה לא
בקוונטים.
יודע את זה.
הוא לא מופיע בקוונטים.
אולי אתה לא יודע שהוא מופיע, או שהוא מופיע ולא מופיע בו זמנית, זה קוונטי.
יש כל מיני שמות משפחה שאתה בטוח שצוחקים עליך, כמו קושי, זה כאילו קשה. אני נגיד בווקטור פוינטינג, אני לקחתי מלא זמן לגלות שזה לא כזה מצביע, זה קרוי על שם פוינטינג.
מה באמת?
תקשיב,
כן, כן, זה קרוי על
מתי
שם...
עשית שדות? אתה חושב לא עשית שדות?
לא, לא עשיתי סדר.
תקשיב, מעיין באתר של הקורס אצלנו שנה שעברה, כתבה וקטור פוינטינג אבל עם I ולא עם Y.
באמת? אז היא לא יודעת את זה עד היום.
אז היא לא יודעת את זה עד היום.
מה קרה?
אמרתי לו על זה שמעיין באתר של הקורס כתבה וקטור פוינטינג עם I ולא עם Y, כי היא חשבה שזה פוינטינג מלשון הצבעה.
ולא, יש שם משפחה. האמת שזה מצחיק.
זה
לא, קוראים לו פוינטינג.
רק שאתה חושב על זה שמרצה, שמרצה
כן,
הקורס.
היא לא יודעת את זה.
היא לא יודעת.
זה משהו כבר שאתה, כשאתה מלמד את הקורס, הייתי מצפה שבזה.
בדיוק.
את ההיסטוריה של הדברים.
בדיוק.
ביי ארדן, תודה. ביי גילה.
Bye. This one?
היה סבבה עוז?
כן, היה תענוג.
אחלה.
So this problem.
This problem.
Yeah.